Welcome, everyone. For today's prep, we're going to keep looking at line integrals, but now we're going to look at line integrals for vector fields. And we're going to start with the definition. So let's read through the definition here. And actually, this has a few things. First, the definition, but also how we're going to calculate these types of line integrals. So we're going to let f be a continuous vector field, capital F be a continuous vector field, and we're going to have some smooth curve C. And we have a vector function that describes this curve. So this vector function, this is our parameterization of that curve. And then, we're looking at a section, so over some interval from A to B. Well, we're going to define the line integral of this vector field f along curve C. And so the notation that we're going to use for this is right here. This is the notation. So we're calculating the line integral of vector field f along curve C, and then this dot here, this is a dot product. And so the differential here, dr, well, we'll see what that is. So this is the notation. So this is the line integral of a vector field f along curve C. Now, how we're actually defining this, the actual definition here, is that we're defining this to be the line integral along curve C of vector field f dot product with the unit tangent vector. So this is just a line integral for a regular scalar function here. So if we remember, f dot t, so t is the unit tangent vector. For curve C, for our parameterization. So we have that parameterization r of t, and t here is the unit tangent vector. So when we take a vector field and when we take a vector and two vectors and we calculate their dot product, this dot product is a scalar function. So the vector field f dot product with this tangent vector, this is a regular scalar function. So this line integral that we're calculating here, this is just a line integral of a scalar function. So f dot t is, the output is just a number. So we have just a regular kind of function here that we're doing the line integral of. So this is the definition part. So this is how we define the line integral of a vector field. Now we could calculate it like this, but generally how we're actually going to calculate this is using a definite integral, just like we did with regular line integrals. So the middle part here, this is how to calculate. All right, so we're going to write this line integral as a definite integral from A to B. And we're going to take our vector field and we're going to plug in the parameterization of our curve. And then we're going to do the dot product of that with r prime. All right, so let's see an example on how to do this. And then we'll come back and we'll look at this this definition a little bit more. All right, so let's look at this line integral. So we're going to calculate the line integral of vector field f along curve C. And again, this is a kind of like a dot product here. Our vector field in this case is, well, it's a three-dimensional. We're in three dimensions here, so it's f of x, y, z. First component is x, y. Second component is y, z. And then the third component is z, x. And C, the curve that we're calculating the line integral over, it has parameterization x equal to t, y equal to t squared, z equal to t cubed, and t is going from 0 to 1. All right, so let's calculate this line integral. So this is what we want to calculate. How we're actually going to calculate this is we're going to write this as a definite integral. So first of all, our parameterization runs from 0 to 1. And then we're going to take our vector fields and we'll plug in our parameterization. And then we'll do the dot product with r prime. And this is the definite integral that we're going to do. So it helps. We kind of want to figure out all the pieces here, figure out all the pieces here, and then we'll just work out the dot product. So let's see what we get. We're going to do the integral from 0 to 1. And let's write out our vector field. So if we look at our vector field, it's the first component is x times y. So I'm going to write this as a column vector, and then I'll write the r prime as a column vector as well. Actually, why don't we start with r prime? Easier to do. All right, so r prime. We're just going to differentiate each of these components. So first of all, derivative of our x component is 1. Then the derivative of our y component is 2t. And then the derivative of our z component is going to be 3t squared. And so if we kind of remember back, what r prime actually is, this value for, or this thing for r prime, this is actually x prime, y prime, z prime. Or if we're in 2 dimensions, x prime and y prime. All right, so this is the derivative of that vector function. So we just differentiate each component, and that's what we have here. All right, so now let's actually plug in our parameterization into our vector field. So our vector field, the first component is x times y. Well, we're not going to use x and y. We're actually going to plug in the parameterization. So we're going to have t times t squared. So x times y. Then our second component, y times z, we're not going to use just y here. Actually, we're going to use t squared. And we're not going to use just z. We're going to use the value for z, so t cubed. So when we fill that out, we're going to get t squared times t cubed. And then we do the same thing for the last component, z times x. So my x here is t, so I'll fill that in. And then, again, my z value here is t cubed, so I'll fill that in for the z component. So when I do this, we get t cubed times t. All right, well, let's simplify all this up and then calculate the dot product. So first of all, if we do all the multiplication here, we're going to end up with the integral from 0 to 1 of t cubed, t to the 5th, and then t to the 4th. And then if we do the dot product, we're going to have the integral from 0 to 1. And with dot products, we kind of just multiply across and then add up the results. So t cubed times 1 is going to be t cubed. T to the 5th times 2t is going to be 2t to the 6th. And just be careful. My plus signs kind of start looking like t's. And then we do the same thing with the last component. T to the 4th times 3t squared. That's going to be plus 3t to the 6th. And then we're integrating with respect to t. All right. Well, now this is just a regular definite integral. And we can actually combine some terms here, simplify this down a little bit, and then just do our integration. So if we do combine those terms, we end up with t cubed plus 5t to the power 6. Get the antiderivative, we end up with 1 over 4 t to the power 4 plus 5 over 7 t to the power 7. And then we're evaluating from t equals 0 to t equals 1. And when we plug in, we end up with 1 over 4 plus 5 over 7. And there's the value of our line integral. And that's the idea. Is when we do this, when we calculate the line integral for a vector field, well, first we need the parameterization for our curve C. In this example, we were given the parameterization. So that's the first thing we need. Just like our regular line integrals, we needed to have that parameterization. Once we have that parameterization, then we calculate r prime. Just like we did here. And that's just differentiating each component function. And then we also need to plug in the parameterization. That's kind of like the third thing we do. Into our vector field. And then once we do that, then we have a dot product to do, and then just a regular definite integral. So really the three main things, though, that we have to do to get started. First, we need the parameterization for our curve. That's absolutely, we have to have that to use this formula. Then r prime, we can just differentiate each piece, and then we plug in the parameterization into our vector field. All right, so that's an example of how to calculate it. But let's just see where this formula comes from. So let's just pop back up here. So let's suppose that, this is the notation we're using, but this is actually what we're calculating here. This is the definition. This is what the line integral of a vector field actually is. So let's start with this piece. So we're doing the line integral of our vector field dot product with the unit tangent vector with respect to the arc length differential. All right. So when we do this, what is the unit tangent vector for a curve? Well, this is we did this a while ago at this point, but hopefully remember. But it's r prime of t divided by the length of r prime of t. So this is the definition of the unit tangent vector. It's the derivative divided by the length of the derivative. And that divided by the length, that's what makes it a unit tangent vector. R prime is just the tangent, and dividing by the length makes it the unit tangent. So that's t. Actually, let me normally do tangents in red. What about that differential, ds? Well, that's something else we've already seen. So ds is the length of r prime with respect to t. If you remember back, ds was, what was it? Well, it was the square root of x prime squared plus y prime squared, and if we're in 3 dimensions, z prime squared, and then we multiply by dt. And that's what this gadget is. It's the derivative for each of our component functions, and we square each of them, add up the results, and then we do the square root. So that's what this is. That's the length of r prime. So when we calculate this, the lengths end up canceling, and we just have a regular definite integral then from 0 to 1. And because we're integrating with respect to t then, once these cancel, then we just need vector field f in terms of t. So we plug in. So the main thing here is just looking at what t actually is and converting this arc length differential, and we can see how we actually get this formula on how to calculate these things. Well, if we work out the dot product, it turns out that another way we can think of how to calculate these vector fields of a line integral of a vector field is so if we write our vector field with component functions PQR as, and let's write it out as a vector here. Well, when we do the dot product with r prime of t is just the derivative of the x component function times the derivative of the y component, or the derivative of the y component, and then the derivative of the z component. So we just differentiate each of the parametric equations there. And so if we calculate the dot product, we end up with x prime times p, which we can also think of as just p times the dx differential. And then when we do the dot product here, q times y prime, well, y prime is the gives us the differential dy. So we have q times dy. And then same thing for the last component, r times z prime. Well, we can think of that as r times the dz differential. And so another formula on how we can calculate line integrals for vector fields is we just look at these three separate line integrals along our curve C. So we integrate the p component function of our vector field with respect to x. We integrate the q component function of our vector field with respect to y. And then same thing with the r component function. And then just add up the results. So you can do it either way. Probably going to stick more to this one in our, in the examples we do, though. All right, so that's going to do it for today. In class, we're just going to see an interpretation of what we're actually doing here when we're calculating the dot product of our vector field with the unit tangent vector for our curve. So we'll kind of provide some interpretation for what this line integral is actually doing. All right, so we'll see you then. Bye-bye.